The next event we'll have will be in a couple of months. And before introducing our wonderful speaker today, I just want to call out all the volunteers who helped make this a really successful event. Thank you, Brian, Milano, and Antariksh for setup, Raylene and Stormy for food, Burchette and Yua for directing traffic, posting signs, Alyssa and Ravens, who might be still outside, for checking people in, Hongchi, Mohit, Jason, and Amit for helping coordinate. Thank you, everyone. I'll now introduce our speaker for today. Paco Nathan is an O'Reilly author and an advisor for Amplify Partners and Galvanize You, with expertise in distributed systems, machine learning, functional programming, and cloud computing. He has 30+ years technology industry experience, ranging from Bell Labs to early-stage startups. And in 2015, he was cited as one of the top 30 people in big data and analytics by Innovation and Enterprise. This is actually Paco's second visit to BloomReach. He was here a few years back to give a talk on cascading. We very much enjoyed having him at our previous talk, and I personally had the privilege to attend a training he conducted on Spark. And I really enjoyed his anecdotes about how computing was in the 90s, how things have changed, how cloud computing has really evolved to what it is today. So we're very happy to have Paco here. If you could all join me in a round of applause for our guest speaker.
Thank you. Thank you for the meeting.
Thank you.
Oh, wonderful. Thank you. Thank you very much. I appreciate it. Let me turn this one off. Got it. Okay, great. Alrighty. Can you hear me okay? Great, great. Let me set this off to the side. Thank you very much. That's very kind. I look forward to checking that out. Well, wonderful. I really appreciate being able to come here tonight to present. And we've been having some excellent conversations just about Spark and machine learning and a wide range of things. I look forward to a lot of other conversations tonight. The topic here is about graph analytics, but we were talking about streaming and machine learning and architecture and all. So I'm open to hearing a lot more about these different topics. My name is Paco, and I've got my Twitter handle up here, Pacoid. That's usually a pretty good way to get a hold of me. I've also got some contact info at the end of the slides, and I'll be publishing these on SlideShare tonight. We'll send out a link about it. All right, let me get this going. Hello. What do you need? Do I need? I need to click. Okay, great. Alrighty. So I wanted to give, first off, an overview about Spark. How many people have used Spark before? Okay, good. So I'm going to show not so much about the background and getting started on Spark, but more about some of the use cases, and then from there, do a deep dive into the graph analytics aspect of it. So to start, the big idea about Spark is that we've been doing all this work with Hadoop, big data, batch on clusters. That was primarily built around the notion of what a data center looked like roughly circa 2002, 2003. Hadoop came out of MapReduce, and that was really what Google was trying to do to contend with spinny disk failures when you had thousands of servers required for a particular workload. So, Hadoop took off, and I enjoyed leading teams doing a lot of Hadoop work early on. Got started with that in 2007. And by about 2008, I was leading an analytics team at an ad tech firm called AdKnowledge. We were one of the largest Hadoop use cases in the cloud. Spark came along about a decade later. So Spark came along really starting out about 2009, but it went open source in 2010. And it's really hit its traction as of the last quarter of 2013. So you see that there's about a decade between the time when MapReduce was being formulated and when Spark was really getting its traction. And a lot of that has to do with Spark being an update in terms of a different generation, a decade later, of hardware. In data centers now, of course, you have multi-core, large memory spaces, SSDs, much better networking, et cetera. All these kinds of resources are much more complex than what MapReduce was originally trying to address. So Spark is about being able to take advantage of more complex resources and get better pipelining across a cluster. I'm not going to go into a lot of detail about the internals of Spark or that kind of background, but the main thing I want to say is that underneath Spark, in the core, there's a data abstraction that gets used over and over. It's called a resilient distributed data set, an RDD. And effectively, this is a vector. If you have a large vector of data and you can distribute that across a cluster and then apply functions to vectors, this provides the essential abstraction for Spark, and it gets reused throughout. So we can do functional programming, of course, with this kind of model. You have some sort of vector of data, and you apply functions, chain them together to build a pipeline. That fits very well with Scala. You have your closures where you have your business logic. It fits very well with Python. You can do this now nicely with Java 8. R is another one that's coming along, et cetera. If you have RDDs, then you can build other abstractions on top of them. So what's come out most recently is something called a data frame. How many folks here work with pandas in Python? Or say R, working with data frames in R? It's basically the same idea, it's just it's distributed. So given that Spark is supporting Python and R, we wanted to have some parity between how people are already working with pandas or working with data frames in R to leverage a similar kind of way to build workflows and pipelines. So the data frame abstraction is built on top of RDDs. You can still get to the RDDs underneath. But you can think of a data frame as it's higher level abstraction. It has more metadata, more information about the data sets you're trying to keep. And we can leverage that for a number of reasons, notably how to do better optimization, how to do faster serialization. What's coming out now is actually a project called Tungsten, which will override a lot of the JVM garbage collection, actually moving a lot of the large-scale data, moving it off heap and doing memory management directly. So data frames are a very powerful concept. Now, if you have a data frame, it's very simple to go back and forth from that abstraction into SQL. When we talk about SQL, effectively it's a functional programming language. It has some constraints, but there's a lot of functional aspects to it. The big thing, though, is if you know what type you have for the different columns in a data frame, then you can register it with a catalog and make it look like a table and do SQL queries where the data frames are in the from clause. The results coming out of the queries are also data frames. So it's a very convenient abstraction to go back and forth between functional programming and SQL. Anybody here do work with .NET? Okay. Nobody does. Anybody here heard of something called LINQ in the .NET world? Okay, great. There's a great abstraction there if you're doing really complex queries in SQL Server in Windows. Then there's a way of taking and unwinding the queries into F# with this thing called LINQ. It's a way of providing programmatic control over queries. So it's a way of bridging between SQL and functional programming. And a lot of those notions were used in something called DryadLINQ, a project out of Microsoft Research, which was excellent. It's kind of a generation beyond Hadoop. It helped to inform Spark and other related projects. Now, another thing is with streaming, of course, when you look out in industry today, we know how to do batch. We've been doing a lot of large-scale batch processing for a number of years now, based off of open source frameworks. But more and more, the value is in real time, some type of streaming apps. And we see this across many different verticals. There's an approach called microbatch that came out of Google. So there's the Millwell project at Google, which really kind of set the bar for this. It's very, very advanced work. A very similar type of approach, though, is being used in Spark, where you have microbatch. You have receivers bringing your data in real time, and then you have a time window. And any data that comes in off the receiver during the time window is an RDD. It's a D stream, but effectively it's an RDD. So we can start to apply all of the functional programming, the SQL, MLlib, et cetera, into the streaming context. Also, if you take a look at machine learning at scale, we've had machine learning, of course, with Hadoop, a lot of very interesting ways to be able to take and build models and score them at scale. Projects like Mahout and others. But what's difficult is to be able to actually train at scale. If you have a billion elements, you want to build a logistic regression model, usually you would have to subsample and then build your models off the sample. But we're seeing more and more kinds of use cases where they don't want to sample. And so MLlib is an approach of taking and building out vectors, either dense vectors or sparse vectors, even more interesting. And then effectively, those are RDDs, or data frames. So if you can think of the training vectors that you use to build a model in machine learning, that also fits with the data frames in the RDD model. GraphX is what I'm going to focus on tonight. I'll go into that in more detail, but it's a way of doing some type of graph analytics off of this same kind of data abstraction. And then in addition as well, there's packages. So the Spark project now is incorporating third-party packages in a more formal way. Getting new code committed into Apache is, there's a lot of I's that need to be dotted and a lot of T's that have to be crossed to go through all the formal process of getting code into Apache. So Databricks and the Spark project in general put together something called sparkpackages.org, and there's a Maven repo that's associated with it. So if you want to add some type of library, provide third-party support, put artifacts in it that people can put into their POM files, et cetera, that's a great way to handle it and not have to go through the whole lengthy process of doing commits through Apache. And there's formal ways of bringing in packages off of that platform to run in your Spark context. So a lot of the rhyme and reason of Spark then was to take a look at the data centers a decade later, leverage the new kinds of hardware, apply the new kinds of software and software engineering approaches, functional programming in particular, Scala, et cetera. And from there, build out a very general purpose engine that could satisfy the requirements of SQL, streaming, machine learning, graph, et cetera, et cetera. And this way you can build up workflows that have a number of different types of aspects without having to jump around between different platforms, without having to pay a lot of integration cost. So that's a lot of the idea of Spark. Now, I've kind of gone over a number of these points here, but we do see some distinct contrast between what Hadoop, MapReduce, have been doing and the benefits that we see in practice with Spark. A lot more streamlined kind of cluster throughput, if you will. A lot better integration of different use cases. Functional programming results in a reduction of cost, because usually when you have functional programming for big data, you see about maybe 3-to-1, sometimes 10-to-1 reduction in code volume. And there's a lot of software engineering reasons why you want to reduce code volume, of course. The proof, though, is here. I don't know if anybody's seen this before or not, but last fall, Reynolds Chen and others from Apache Spark set the new world record for something called the Gray Sort Challenge. This had previously been held by Yahoo. Yahoo had used a cluster of over 2,000 machines, and they'd taken 70+ minutes to sort 100 terabytes in a very well-structured, repeatable kind of evaluation. The Spark team came in and was able to do the same Gray Sort 100 terabytes in 1/3 the time with 1/10 the size of the cluster. And an interesting thing here is that Yahoo never really published what type of hardware they were using specifically. They did it in a dedicated data center. With the new world record, this was done on AWS, and there were 3 pull requests that were required. So if you want to repeat this, you can. The other thing is that a lot of the memory features for Spark, which is where you get a lot of the speed, they're actually turned off to be able to have a fair comparison with what Yahoo had done previously. And the team went further. The Gray Sort Challenge is 100 terabytes. The team went and did a petabyte sort. And you see a pretty much linear ramp on the metrics. It's about 30x improvement overall. And just some cheerleading slides here, but definitely Spark has hit this inflection point in late 2013, and it's become one of the most active projects at Apache, both in terms of the amount of contributed code, but also the number of different contributors. O'Reilly did a case study recently and found that the median salaries for Spark were higher than the other big data projects. So you might want to show this to your boss, learn Spark, deploy, and then of course get a raise. Donnie Burkholz, had done this interesting comparison, taking a look data mining off of Stack Overflow. And you see this inflection point in late 2013 where Spark just really takes off. And we've seen that as well in the meetups, in the conferences. It's just really exploded. More formally, though, Databricks and TypeSafe did a survey about big data programming and taking a look at the different languages, different use cases. TypeSafe really did a nice job in this, so I'd recommend checking out this case study. Okay, so that's a little bit of background about Spark. We've got a lot more materials if you want to get more of an introduction, a deep dive. But I want to focus on graphs. So GraphX. GraphX is a newer part of Spark. It's been, just recently, it's come out of alpha. So the high-level APIs are stabilized, but what's underneath it will go through a lot of changes. There's a lot of optimizations ahead. The main point, though, is that there had been a postdoc, Joseph Gonzalez, who was one of the authors of GraphLab. He'd been a postdoc at Berkeley, and he put the GraphLab API on top of Spark. There had also been people that were doing work with something called Pregel. There was the Pregel paper out of Google, of course, which was used for Giraffe and others. And they put that on top of Spark too. So taking these two together, it became GraphX. And so now we have very convenient metaphors for leveraging Spark to do graph algorithms, but also get the benefits of Pregel, a very succinct code for building algorithms. The class of problems that are appropriate for this would be similar to what you see with GraphLab. If you've read the GraphLab paper, actually that's the first one I have on the next slide, paragraph, they talk about graph parallel systems. And so how can you really leverage graphs at scale if it will satisfy the constraints of a graph parallel system. The other thing about GraphX is a distinct emphasis on integrated workflows. It's not just about graph processing. Spark is also about SQL and machine learning and ETL and all these things. So the focus is really on how to tie the different components together into one app that handles all the different parts of the pipeline. And so a lot of what we've learned about working with graphs has fed back into Spark proper as far as optimizations. So here's some references that would be good to take a look at if you want. The GraphLab paper up at the top, followed by the Pregel paper from Google. Ankur Dave is the person who's really leading on GraphX now, and here's a recent talk that he did back at Spark Summit in New York. And also another a machine learning PhD out of CMU, Joseph Bradley, who joined Databricks last year. He just did an LDA implementation with GraphX. So that's, I think, another really good illustration of what can be done with this. To show how to handle graphs in Spark, basically these three lines. If you take a look at what composes a graph, you've got nodes. You've got some set of nodes, and then you've got the connections between them. So if you can specify a data structure for the nodes and create an RDD, that's the first line. So we must have a unique identifier for each node, that's the long, and then some other type of data. It's arbitrary. This is a strongly typed system, so whatever type you have in there, that'll be the node data, ND. Now, the triples that connect the nodes, you've got the edges as well, and so we'll define that in RDD. We have a special type of class called edge, part of the GraphX package, and it takes as a parameter, it'll have some type of attribute data, so some other type, ED. You take these two RDDs, you compose them together into a graph, and then you've got effectively the type signature, ND and ED, for your graph. Now, as you apply functions to these, you get RDDs coming out as the result set. So it ties in very nicely with the whole functional programming metaphor. To show an example then, let's say that I've got people, and I've got a case class there. How many folks work in Scala, I should ask? How about Python? How about Java? Okay, good. It's a nice distribution. I'll show a little bit of both, but probably more Scala than not. If you have some Java background or Python, this should apply very well. But let's say we have an array of people. For each person, we've got a unique identifier, a long, and then we've got this other class that has their name and their age, so a string and an integer. So I'll define that as a node array. And then I've got an edge array that defines the connections between them. So for each edge, I've got two identifiers, the unique identifiers for two nodes, and then some attribute. In this case, the attribute is just an integer. I'll take and define those arrays, and for each array, I create an RDD. Down there, you see where the parallelized node array and parallelized edge array. And then I take and compose them into a graph. And so I've got this graph G, and now I can apply functions, different types of transformations, et cetera, to that graph object G. And I'll be running my graph algorithms in parallel. In this case, I do a very trivial traversal of the graph. I just filter it, and I say, if the edge attribute is greater than 7, then show me which edges. And so it'll print out the ones that have high value edges. So that's a very simple kind of graph traversal. If I want to go and do something more complex, though, if you've done work with graphs, you've probably encountered Dijkstra and other related types of algorithms. Of course, this gets used a lot throughout industry in terms of routing problems, scheduling problems, various types of cost optimization. Here I've got a very simple graph that shows 4 nodes and the cost of traversing between them. You can think of this as being essentially the Google Maps directions problem. If you want to get from point A to point B, what does it cost to take that route? And what are the different stops along the route? So let's check out some code. Let's see here. If I wanted to show an implementation of that, I'm going to cut over here into what's called Databricks Cloud. Essentially, this is a notebook. How many folks have used IPython Notebook or seen that? Okay, this is a lot like IPython Notebook. It's got Spark clusters behind it. And I'll dig up here, let's see, GraphX. So the implementation for this simple example I'd shown here, I just do a very simple traversal of that first graph. Now, if I want to do something more complex, I'm going to have more illustrations here, but the graph that I'd shown with 4 nodes and the cost between them, I'd like to run an SSSP, a single source shortest path. So let's say that we want to find the best path back to node 0 from all the other nodes. Here's an implementation of it. Basically, I create my graph here like I'd shown in the diagram. I've got 4 different airports listed and some cost between them. And I create the node RDD, the edge RDD, compose them into a graph, and then I create a shadow of that graph where I lock down the vertex that is my goal, vertex 0, node 0, and then I set the cost of any other route to positive infinity, basically, worst case, and then from there I optimize. So the optimization is just a few lines of Scala. Here it's implemented in Pregel, and so an SSP implementation is pretty quick. But basically, you're sending these messages back until you find the best routes, and then print them out. So here, going from 0 to 0 is a trivial case, 0 cost, null route. And going from node 2 to 0, it's a direct connection, cost of 1. From node 1, it's a cost of 2. From node 3, it's also a cost of 2, but a slightly more complex route. This is the kind of thing that Google Maps, FedEx, UPS, they do this all day, every day. And so there's a lot of great industry use cases for large-scale graphs. Let's take a look at something a little bit more complex, though. So let's see here. Go back. Great. So let me jump out into graph analytics in general. Not just Spark, but just taking a look at the industry in general. So many real-world kinds of problems can be represented as graphs. It would be the natural way of representation for a computable problem. And also, graphs in general can be converted into sparse matrices. I'll show this in a bit, but you can generate some type of matrix to represent your graph and then apply linear algebra techniques to operate on the matrix instead of traversing all through the graph. And if you go to companies like Twitter, their revenue analytics are based off of this idea. If you do take and represent your graph in terms of matrices, then it may be very efficient to go out and compute the eigenvalues and eigenvectors in your matrix, and from there be able to get some good metrics about your graph, or how to factorize the matrix to be able to optimize your graph. The other point I should make is that if you really get into this, beyond the simple graphs, if you start to have a lot of different types of attributes across between different nodes, then it won't just be this simple case. Instead, you quickly get into the case of using tensors. So that's a much more general way of handling. And that's an interesting point with respect to Spark. Okay, so I talked about going from a graph to a matrix. So here we've got a very simple graph like we've shown before, 4 nodes. And I can take and create what's called an adjacency matrix. Basically down there you can see there's a 1 if there's a connection or a 0 if not. And this matrix has some special properties. It's symmetric. It has real eigenvalues, and I can use these to find things like the diameter of the graph. There's a whole body of math called algebraic graph theory that gets into this. And again, very interesting industry use cases. Now, if you really want to jump into working with matrices, there's some great stuff out there. University of Florida has a sparse matrix collection. They've got MATLAB that shows how to visualize all these different sparse matrices that they've collected over the years. And they actually use these as test cases. I'll point out a couple of books here. Norman Biggs is kind of a standard book on algebraic graph theory. There's a new one coming out of a company that's called Uncharted Software. I've worked with some. Richard Brath and David Junker. Very interesting graph visualization work. A lot of it based on Spark and Spark streaming. And I've got a video also that goes into some of the industry use cases for this type of math and these type of frameworks called Just Enough Math. I mentioned about tensors, and this is kind of looking forward that as we get into more and more complex types of graphs, we rapidly get into tensor problems. And there is work currently in terms of tensor factorization. Anima Anand-Kumar at UC Irvine, there's a great interview with her on O'Reilly Radar, and she had just done a talk at Strata Hadoop World about doing really probabilistic approaches for solving tensors in general case. And she's actually got a job rec open now out of UC Irvine if you want to implement tensors on Spark. Or at least I heard it was still open. So not to be recruiting for, of course. There's also David Gleich, who was out of Stanford, but he's at Purdue now. And he had a recent paper that also got into using Spark and Hadoop for tensor factorization. We're interested because if we can get these libraries and make them general case, it'll have a huge impact on the types of large-scale machine learning problems that we can try to address with open source. And actually, it'll really reduce a lot of the code that we have to build because this is much more of a general case kind of approach. So I'm very eager to watch these people and see what these and others are doing with tensors. Okay, so let me jump in from here into something more practical. There was a project, it's on GitHub, it's called Xdo. And the idea is that if you take a look at any of the Apache developer communities, you've got a lot of interesting data. If you look at the, for instance here, if you look at the Spark user email list or the Spark dev email list, they're generating a lot of data. The data has interesting natural language processing possibilities, interesting time series, interesting geospatial, but in essence, there's a lot of linked data there as well. So there's this project that we've created to be able to point at any Apache developer community and then start to surface insights about the structure of the developer community. Yeah, that's pretty much what I just said there. And it's using Spark and GraphX. At the end of the day, what it produces is feedback for the understanding of the communities, such as leaderboards and rankings. So I've got some links here. I've already got these open. But if you want to follow along later, the only thing that would be hard to get to is, of course, the Databricks cloud. But I've got all the code exported from this actually in the GitHub repo. So first off, we can take and look at a given developer community. Here we've got Spark-user, and apply this open source code to come up with data sets. Looking at, actually it's not dev at Spark, it's actually user at Spark. But looking at this, it runs at about 2,000 messages per month. And so that would be about 18 megs per month. It's not huge data. There's a parser as part of this project that will scrape the Apache sites and come up with a data set. and like I say, it's just megabytes, really. I collected the previous 6 months worth of activity, and there's 2,000 senders in the community. It's about a 2 million node graph with over 3 million edges. The graph itself is slightly larger than you'd probably want to do on your laptop if you're doing any sophisticated kinds of algorithms. So it's good for this graph parallel kind of system here with Spark. So to show the workflow then, basically we've got some process outside of Spark, and I think that's an important point. We've got some external process. Let's say that if we talk about microservices, this would be a very good example of where to apply microservice architecture for machine learning. So we've got some separate process that's doing the scraping and the parsing of the email messages. Email messages are difficult because you've got a lot of quoted text that you want to pull out. But at the end of the day, that produces some JSON. And it doesn't have to be repeated. Once you've scraped a given message, you just store it. You don't have to work with it again, so it's immutable data. But from there, then we have a more interesting pipeline that goes into Spark. We'll do some Spark SQL to do data preparation. We'll explore a little bit, data exploration to surface some metrics about the community. From there, we'll do some featurization and some graph algorithms to surface better insights about the community. So this first part here is not such big data, but the pipeline starts to explode. When you take a look at the graph processing downstream, this is where you get into fairly large data. So the way this works, yeah, as I said, we're basically going to crawl and then do some filtering, a little bit of NLP, and drop it down into JSON. That code's online. I'm not going to go into the NLP processing too much, but it's based off of using text blob on top of NLTK. It's in Python, and it also uses WordNet, a little bit of semantic relations analysis. At the end of the day, each message then will come out with some JSON document like this. So the part of the linked data comes in because you know the threads, and you know who's responding to whom, essentially. Okay, so we do that. Like I said, we do a little bit of natural language processing with TreeBank and WordNet, and come out with a really lightweight parse, and then generate this down here as our source data for the Spark pipeline. Okay, so to show some code, I go back over here under where were we? Exto ETL. Is this big enough to see back there? Okay, great. So this is implemented in Spark in Python because I wanted to reuse a lot of popular Python packages for NLP. So down here, I load in the JSON with just a few lines and create a data frame. I register that, and so now I can do SQL queries against it. Take a look at some of the metrics. Yeah, like I say, 13,000 messages over 6 months. Here's the sample message, just the raw JSON. And but the interesting thing with Spark, though, is it actually uses the JSON to infer the schema. So it'll take a union across all the JSON docs, and then that's a schema that you can apply to query. So I'm going to ask a few questions in terms of just typical BI kinds of queries. What's going on in this community? Who are the senders? Actually, what I do is I'll collect that out. I'll basically do a little bit of ETL here, and I'll figure out who the distinct different senders, developers are in the community. And for each one, I'll assign a unique ID. And I'll collect that as a map and then use this for some processing downstream. Okay, so I've got unique IDs for all the senders, their names, their email. So who are the ones who are sending the most? Who are the top K? Basically, this is a word count, if you've ever done word count before, but it's pretty much like that, just finding out top K for senders. And I can print it out, or I can take and query it with SQL. Now, the interesting thing with Spark is that until you actually need results, nothing happens. There's lazy evaluation. It builds up a DAG of what needs to be processed. So I can do this whole big ETL pipeline, all this processing, but until I actually run the query, nothing happens. And because it's deferred, you have a lot of opportunities for being able to do predicate movement, optimization, code generation, push down predicates, et cetera, things like that. What this comes out and says is that a friend of mine, Sean Owen at Cloudera, is the 621. He's the most frequent one. And Akhil Das at Sigmoid Analytics comes in number 2. Michael Armbrust, who created Spark SQL, number 3, et cetera, et cetera. So, we've got a little bit of a leaderboard going on here. Okay, that's good. Let's take and do some other processing here. The timestamps were represented as strings. I'd like to parse those and get some kind of numeric timestamp and take a little bit of a look at the time aspects of this. So I'm going to go in and parse the timestamps, look at some deltas there, create a data frame out of the transformed results, and then query it. And what this shows me is, okay, here's Sean, and here's the duration of his engagement. Basically, he's there every day. And Akhil right on his heels. But the other people, it kind of levels out here. You kind of see, you get this baseline. Okay, interesting. Let's find out who's talking with whom. So here we can take a look at the different threads and see who the sender and the receiver are. Now we start to build up some of the graph aspects. And of course, there's going to be repeats. There's going to be extended conversations. Some people actually answer their own message. So here we had one person who answered his own message 23 times in a row. These things happen, of course. And let's see, what else here? Okay, let's take a look at, more aspects of who's really being active as a sender. I'd like to take a little bit more look in terms of the conversations, not just the senders, but where's the couplets between people. And so a little bit of transforms here. We'll do a query on that to find out the couplets. And there, you can see that Akhil Das is responding to Haas. What this is interesting is in terms of a competitive analysis, which companies are most proactive answering certain types of questions. So that's an interesting thing when you look at the developer community and see these different vendors, different consulting firms, how they're engaging. Okay, great. So a few queries, but let's prepare to do something more significant. So here, I'm going to take and structure this to have a node RDD, or data frame for an RDD, and then an edge data structure as well. And then we'll take and create these as data frames and save them as Parquet files. How many folks are using Parquet here? Anybody? Really, it's a best practice that we recommend with Spark. It's a great way of preserving the metadata, but there's also great compression because it's a columnar store, and it accepts predicates. So you might have 100 fields in your data structure, but when you query, you might only need 3 of them. And it's smart enough to actually push the filter scan down so that it only deserializes and decompresses the fields that you need. So you can get some great efficiencies there. Okay, great. So I've created a social graph of this data set as 2 Parquet files for Edge and Node, respectively. Let's do something more. And this is the gist of the talk is something called text rank. So what I'm going to do is take a look at, for each message, I'll take and segment it into sentences. And for each sentence, I'll segment that into words. For each word, we're going to scan and figure out what the part of speech is, and then take a look inside of WordNet to what we call limitize it. Basically, find out what the stem is. If it's a plural noun, find out what the singular form is. If it's a verb, find out what the infinitive is, or the root is. Okay, so we come out with these data structures basically per sentence, per paragraph, and once we've got those, then we can start to generate, essentially we create a skipgram. We traverse each sentence, and we take a look within a window. It's actually set to 3. We take a look at the verbs, nouns, and adjectives that are within the skipgram window, and link any of those together. And then we take a look at words that have common meaning. So if you see a plural and a singular of a noun in the same paragraph, you create a link across. You can go even further. If you're familiar working with WordNet and different word sense and metonymy, then you can take and do like hypernym links and leverage the semantic relationships, actually do a random walk on the graph. You get better convergence that way, but I'll get into that later. Anyway, long story short, we're going to create a ginormous graph out of the linguistic analysis of the email messages. And this gets pretty huge. So just long story short, this is what each node is going to look like. And of course, the skipgrams determine what the edges look like. But I'll save that off as Parquet files. Okay. And now, what I'd like to show is there's something called text rank. This came out of UNT. Radha Nahasya and Paltereau at UNT, and Radha subsequently got gobbled up by Google and was at Google for a while. She's now at UMichigan. Just had some email back and forth with her. But their idea was to be able to do a lightweight linguistic analysis of any random text, create a graph out of the raw text, and then leverage the semantic relationships there in that graph, basically applying PageRank to that graph. And so then the noun phrases that are most highly ranked, you can think of like pulling a thread and getting out the highly ranked phrases. That creates automated summarization of a document, arbitrary documents. And you can see this, let me scoot down to their example that they published. If I've got some paragraph, I can create a graph out of it, and then I can use that to summarize. So here's the summarization done by an editor on a peer-reviewed article versus the summarization done by the algorithm. It's actually very similar. And so this is interesting because now I can take arbitrary text and be able to use this graph analysis to create my feature vectors for how to categorize the texts. I used this at a company called ShareThis, actually down the street. We did this for a project for Rolling Stone, a custom search engine. We were able to get very high performance ad targeting off of that, actually. Okay. So to build this out, well, I guess first off I want to show here. There's Radha Nahasya and some links to her in the original paper. There have been some different implementations. Jeff Kubina did one. It's up on CPAN, so there's a Perl implementation if you want that. I did one based on Hadoop a long time ago, 2008, and Karen Christensen did one in Icelandic. It's in Java. And here's just kind of a look at the pipeline of what's being done. Also the paragraph that came out of the paper, basically constructing a graph out of raw text. So what we do is we take a sentence, we tag it, stem it, and then we basically construct a graph out of a skipgram analysis of the text. And it's using TextBlob. I highly recommend. It's a layer on top of NLTK, but it's got a much better statistical tagger than NLTK does, and also WordNet, of course, very popular. And then we run PageRank. So to show that in Spark, let's go back here. So I'm going to load in the edge and node data frames out of Parquet. And just for the sake of making this something quick to compute, I'm going to tie it down to one message. I'm just going to look at one message. So I picked an arbitrary ID and filter on that. I build up my edge and my nodes, and then I construct a graph. Let me see, get down here. I construct a graph right here, and then to run PageRank on it is very simple. It's one-line call. I tell it what my convergence threshold is, and I pull the vertices out of the results. Those are the ranks for all the nodes. So basically, for all the words of interest, I have a PageRank now. And I'll do a little bit of transformation in Spark to be able to convert that back, convert the ranks back into a data frame, and then I can query it. So you can see here, memory in this one message shows up pretty highly ranked, persist, et cetera, et cetera. You know, it's a little bit better than doing an M-gram analysis, but it's still not good. It's not what I want. So I'll take these ranks and I'll pull the threads. I'll take a look at summarizing by extracting key phrases based on the ranks. So here I'm going to build up a little bit of a pipeline for that. You can see the raw data. And right here I'll do, well, let me get here's the function to extract phrases, basically aggregating the different ranks for different parts of a phrase together and then sorting those. And once we do that, now we can come back in and query, and we see that the most highly ranked phrase is memory crunch, which is a lot richer view of what this little piece of text was saying. MapReduce operations, iterative algorithm, et cetera, et cetera. So even though I had a very thin piece of text, I can actually extract a fair amount of meaning out of it. And again, by virtue of doing the graph algorithms. If you looked at just an n-gram analysis on this raw message right here, like if I do a word count on it, I get a fairly flat kind of result. Not very good for machine learning features. So that's a lot of the rhyme and reason doing this text rank analysis. Okay, great. Now let's show how we're doing on time. We got about another 10. Okay. The other side of this is social graph. So I'd also like to take a look at the interactions between people and use this as basically creating a foundation for analysis. If I know who is sending to whom, who's replying to whom, and what the nature of their communication is, then I can take and run text rank and find out what are the topics that they're talking about. So basically, this is a foundation for the other to be able to be overlaid. And that's still in progress. But if you want to take a look at graph analysis of the social aspects of it, essentially here I create my reply graph, the parquet that we'd stored first. I run PageRank on that, and I can find out who are the most top-ranked repliers, who are answering questions most actively, and how much are they connected with other people. I can also take a look at the degrees of the graph and traverse that, find out if there are some nodes that are orphaned or some that are very highly connected. And you can do this very readily in Spark and GraphX. If you want to take a look at connected components, et cetera, let's take a look here. So out of an analysis here, Sean Owen came out, of course, being highly ranked. Akhil Das, similar but not exact to just doing a raw query. It's actually a better analysis than just doing a raw query. And you can see the in degree and out degree, a little bit of graph analysis down there. The code for this would be back here. It's number 4. So I pull in my Parquet files, and then I compose a graph. And then once I've got the graph, I can take and run PageRank, query that. And so we can see, here are, during a certain period, here are people coming out. This is actually with a slightly different view of the data that I ran on this one. Also, if I want to do in degree, out degree, et cetera, just get some metrics from the graph, I can do that. And connected components is a call, strongly connected components, triangle counts, et cetera. That's all built into GraphX. Okay. Now, where this is leaning up is there is an interesting paper. How many folks here have ever used LDA, latent dirichlet allocation? I've used it. We used it at a company called InView. One of my colleagues is back here. We work together a lot. We used it at InView to categorize the chats in the chat rooms. And LDA is somewhat sensitive to noise. And in chat, that's actually a problem. So a paper or an article came out recently about using something like TextRank would produce, basically coming up with features that are fed into Word2Vec and then doing clustering off of Word2Vec. Has anybody here used Word2Vec before? So the idea of Word2Vec is you can come up with these rankings of different phrases across a collection of documents, and then you can apply arithmetic on those ranking vectors. So if you take Rome and you subtract Italy and add France, you get Paris. If you take king and subtract man and add woman, you get queen. So you get this kind of semantic relationship based off of vector math. Really interesting work, but it's a nice way of featurizing some collection of documents and then being able to make some inference about it. Or you could cluster and then get topic models popping out. So it's considered to be an alternative to LDA, maybe not as sensitive to noise. Could be very handy for things like ad tech, very definitely. So that's kind of where this project is going. Also, I want to point to some resources about Spark in general. There's a developer certificate that Databricks and O'Reilly have done together, and I'd be very happy to answer any questions about that. It's 40 questions, multiple choice. We're doing another one now for Cassandra, very similar, possibly Kafka down the road too, and others. There's a lot of great community resources. If you look at the community site for spark.apache.org, the email list, the ones that I was analyzing, those are the best resources to be able to get in front of the committers for Spark. All the committers are active almost on a daily basis on the user list and the dev list. So I recommend those. We've got a global event directory and also a YouTube channel for archives of events. Recently, Databricks just launched 2 MOOCs. Anthony Joseph from Berkeley has one in progress. 56,000 people had signed up for it as of the first of the week. And then Amit Talwalkar, who created MLlib as his PhD, Amit is going to launch one in late June about scalable machine learning. So these are pretty popular. They're free. They're in progress. And I mentioned Spark packages. Here's the link to it. But a lot of great resources there. There's also Spark Summit. There's 3 of them per year now. The next one comes up mid-June in San Francisco, and then in Amsterdam in October. And also the Strata conferences. I work on Strata conference. I was at Databricks. I'm now at O'Reilly. I'm still working on some of the same projects. We do a lot of partnership. But we've opened up Strata so that we have not just California, which was the original, we also have New York, London, and now Singapore for Asia-Pac. And some good books that are coming out off of O'Reilly about Spark. A couple of the newer ones there, Sandy Riza, Sean Owen, et cetera, they did Advanced Analytics of Spark. Holden Corral and others did Learning Spark. And a new one out, Mahmoud Parsian did Data Algorithms, also based off of Spark and Hadoop. Here's my contact info. If you'd like to link up on LinkedIn, that sounds great. And I've got other resources there listed, a couple of books. We have some books here. We also have a box full of goodies from O'Reilly, so free books and whatnot. And with that, let's open it up to questions. Thank you very much.
Questions?
Okay. Are you making the data, the Sparks community, the one that you mine from the community, developer community, are you making it available for free to everyone and publicly available, or?
It is. I've actually got it up on a S3 bucket. The data itself, that's when the scrapers and the parsers have run, the raw data is available. I'll have to list that. I think it's on the README of the open source project, but it's on a public S3 bucket.
I had one other follow-up question before I give up the mic. I was a little curious about how you formed the connections between to send a sender and anybody who participated in the developer community emails. The sender and the receiver have a link only if they've shared a message ID?
Right, exactly, yeah. So it was based off the structure of the messages because you'll have the sender, but then you also have the replies. So essentially you have to crawl through the threads and then look. I mean, the original message won't have the complete part, it's just the sender. But then you look at the replies back and connect up from there. There's a little bit of post-processing. I had to do some ETL for that. That's great, thank you. We'll be giving books out as you ask questions. Ask lots of questions.
No, Victor, if you need it for the recording, I'll just put on your mic.
Interesting. Well, you know, cascading is being put on top of Spark now. Cascading 3x will have support for MapReduce, Hadoop, and Kez, and Spark. And so a benefit there, I mean, there are some interesting things that can be done with cascading for enterprise workflows that Spark hasn't implemented yet, particularly when you look at scalding and some of the other layers on top of it. Like Twitter's revenue analytics are pretty much implemented all in scalding these days. So yeah, there's some good benefits. There's also cascading provides more of an enterprise view of like build back and you know, historical analysis of applications running on clusters. Spark doesn't really have that kind of tooling yet. So in terms of scalding, you know, it's definitely got more years. I mean, Twitter's been using this at scale, LinkedIn, eBay. So there's been some really big use cases for a longer period of time. There's some great libraries like Algebird to be able to do monoids to represent your business logic, approximation algorithms, matrix math that Spark is still catching up on. There's better ways to be able to checkpoint workflows. So if you do have a crash, you can recover from a checkpoint. And also being able to basically provide assertions into the workflows so that you can track bad data as it's coming through and shunt it off in a different direction. There's a lot of enterprise-y kind of features, so to speak, that Spark is building, but they're not, I mean, it'll take time. What is that? Books. Okay. We have different books too, by the way. So you got multiple questions.
Yeah, I had a question on the phrase extraction after doing text rank.
Yes.
So once you create a text rank, so you run text rank based on the word graph for each of the words that are nouns, phrases, or whatever.
Yeah.
And then once you have extracted the top words, I didn't understand that step from how you went from there to extracting keywords.
So the idea is that a lot of times when we're doing some type of document classification, we'll use a bag of words kind of model. So we'll basically just segment out the keywords and then throw those into Lucene or Solr or whatever. So this is the idea that we could actually have ranks associated with phrases that have more significance in terms of semantic analysis. And there are other things coming out of here too. I didn't show, but there's sentiment detection. There's other things that are on per paragraph. So basically, we could have a wider array of metrics per phrase. So much richer kind of features. Does that? Yeah.
Hi. So my question was that is there any optimization for GraphX or like you can use Neo4j for graph database? So is there any comparison that you can point out?
Excellent question. Yes, I was hoping to get to that. I mean, there are some different types of graph platforms, and they have their trade-offs. Neo4j is very convenient, very nice integration with Java. It's more suited for doing single node or for smaller graphs. On the other end, there's things like Giraffe, which you can do trillion element graphs like Facebook does. So part of the issue there is Neo4j in terms of scalability, but also integration with machine learning libraries, et cetera. Giraffe, on the other side of the spectrum, what I've heard from the large use cases is it does require overhead, and doing ETL is very costly. Especially getting the data into the graph is costly. With GraphX, it's in between. And so it is addressing scale, but hopefully more lightweight than, say, what Giraffe does, and more closely integrated with what you'd be doing in machine learning. One of my colleagues, TD, Tathagata, just came back recently from Beijing, and he's the author of Spark Streaming, and he was looking at some large use cases, large deployments in China, where they basically take the streaming data and create a delta on the graph, basically look at what's changed on the graph and only do the analysis on that. And that's something that would be inconceivable. I don't know how to do that in Giraffe. That would be very expensive from what I've heard. And the scale of it would be hard to do in Neo4j. So it's somewhere in between the two.
How compared to GraphLab?
GraphLab, excellent. Well, GraphLab has Datto. They've been doing, how would I say? I think that they've definitely done a richer set of libraries on top, and they're more general. They're not just graph now. They're much more general with Datto, and also more mature in some ways. GraphX is newer. I don't think that they're going after the scale quite as much. So what I've seen out of Datto is they're going for more problems that you could run on a beefy machine, as opposed to running on a large Yarn cluster or a large Mesos cluster. It seems to be. I need to get more hands-on. I've talked to some people on the team, and I hope to be working with them more closely. Does that answer? Okay.
How does Spark fit into the real-time, let's say you have a real-time handling of the data
Yeah.
going in live, you could take the examples of how does that Spark fit that?
So the micro batch that they're doing with Spark Streaming, again, similar to Millwheel at Google, what we see is that use cases will get down to about 500 milliseconds. That's kind of a hard limit right now, because if you're in a clustered environment, the network speeds alone, it's very difficult to tell which servers are alive or not based off of TCP/IP. So 500 milliseconds is about the minimum for the micro batch windows. Most of the use cases we see are on the orders of seconds, several seconds for the batch windows. Now, if you want to get much smaller, there are other ways, of course. Something like Storm, you can be looking per tuple, but the trade-off there is that you're not getting the one-time only semantics. If you want to store the data, typically you'll aggregate it. So you're going to end up with something like Triton on top of Storm. Ends up looking a lot more like microbatch. Yeah, there's been side-by-sides where you can get better performance out of Spark streaming. I think Millwheel is, of course, the more sophisticated one out of all of these. There was a great talk at Strata in London last month by Tyler Akito, who's one of the leads on Millwheel, and he compared all of these. But I know the presentation is live. I think the video may be public too, but I would refer to that. So.
In this project that you talked about, what are the typical sizes of graphs that you encountered?
Excellent. Here with one of the most popular Apache projects, it's 2,000 messages per month. And so it really comes out to being hundreds of megabytes, even over a period of a year. So, and that's with a popular project. The less popular projects, of course, have less traffic. So, with this, I could do some of the graph processing just on my laptop. When I prototyped it, I did it on my laptop. But then I moved it out onto a cluster. The big thing, though, is actually the reason I started doing this, my friends at Google who are on BigQuery, they were like, we need big data. And I was like, really? How big? And then we need a graph that's huge. And so like, I think I can generate one. So I wanted to do the natural language processing to create these enormous graphs and let them chew on it for a while. Does that?
One more question. What about the sparsity of these graphs? Have you had any experience with how sparse these are and how that affects your computation?
Great point. Great point. And if you look into the GraphX programming guide, they talk about how they do the cuts and really, some of the parallelism with respect to sparsity of the graph. As far as what I'm measuring here, when I looked at the connected components analysis, I didn't really get a lot of interesting things because, frankly, in the sparse community, everybody was talking to everybody else. There were only a few examples of isolated components. So sparsity, not so much. I would have liked more. When you look at it linguistically, though, when you look at the text rank graph, yes, very much so. And we really leverage that because at the end of the day, there's only so many phrases that are being used in this community. And that's the interesting part.
I have a follow-up question to that.
Sure.
So there are some situations where you create a large graph and then contextually, based on a context or a user session, the graph itself changes.
Yes.
So in that case, you need to actually have it all stored somewhere. The entire graph, all the information, so that you can extract what you need at the time of request. So this is where I think I can split into two questions. The first question is about the real-time applicability of this.
Yes.
Neo4j probably would be more aligned for doing something like this, if because of the speed of access. And the second, or may or may not be, which you can explain. And the second part is, has there been any real application of that you have seen
Yeah, yes. So I'm blanking on Divyandu's name. I'll have to dig him up. But he's at Pearson, and they've been doing really interesting real-time graph analysis for their revenue apps at Pearson Higher Education, where they're taking feeds across the world and then assembling a large graph and be able to optimize for their sales targeting. So it's a great case study with Spark and Pearson. So that would be one that I'd really point to. There's others as well. Now, an interesting thing though about the speed, again, there's lazy evaluation. So I'm building up these data frames out of Parquet. So I have the nodes and the edges in Parquet when they're stored out in HDFS or Cassandra or something like that. And because of the lazy evaluation, I don't load it all in. So if I want to compose a graph and then do some kind of filter traversal across it, again, to take that subset that you were talking about, I could do that without actually doing the evaluation yet. It's not until I actually take an action that the data would come out. So ostensibly, those predicates could be pushed down into the storage layer, which would give a really nice optimization. So that's how I would approach that kind of problem. The other thing is that there's something called Tachyon, and there's a company that's commercializing this. The lead on that, HY, Xiaoyuan Li. Essentially, it's like HDFS, but in memory off heap. So you have the RDDs that are the basis of Spark can be externalized, serialized into this file system, and you've got resilience there. And so then you can be working off heap at memory speed. And if you have a cluster with current class of hardware, you've got a lot of memory space, terabytes. And so you could be getting very large graphs at memory speeds. That's how I would approach that. Does that? Oh, one other point. One thing I should be, when we talk about streaming, a lot of these systems are effectively stateless. Right? They're working with immutable data. And there is a way in Spark streaming to have stateful apps. So effectively, you're leveraging the memory aspects, the memory caching persistence of Spark to create an in-memory key value store. There's something as a call update state by key, where most of the Spark data is immutable, but in this case, no. So you actually overwrite per key. And that way you can have your main data structures in memory and then build the graphs downstream from that, which is a really nice optimization.
Many data sets, like different data sets, you have follow power law.
Oh yes, for the people off.
Yeah. So many real-world data sets typically follow a power law distribution versus a normal, and that is a disadvantage in a MapReduce system where your reducer gets choked with a lot of things. So I was wondering whether Spark overcomes this difficulty.
So very interesting point there. Yeah, if you look at Twitter doing their social graph analysis for the revenue analytics on Hadoop, the synchronization barriers in Hadoop become a problem because of the key value skew. So you can think about their social graph. Average number of followers on Twitter is 200 plus. But then you do this huge social graph on a large cluster. Most of those reducer tasks that aggregate key versus all the followers, they'll complete in seconds. But then you hit Katy Perry and Justin Bieber and Lady Gaga, and they have millions of followers. And so now those reducer tasks will linger. The heavy hitters linger for hours. So effectively, your cluster utilization drops to 0. It's a huge problem with Hadoop. And the thing there with Hadoop is that when it was built, it was because of spinny disk fail. Google published this recently, but if you have say you have a machine learning pipeline and it takes 2,000 servers to run, the average daily failure rate is 10. That's current Google hardware. So you expect to have 10 of those nodes disappear. In 2002, it was a lot more than 10. And after a while, you can't just restart because your probability of completion drops to 0. So MapReduce was very much about imposing these synchronization barriers. You have a flat map operation that lifts the data into memory, parallelizes, you do some processing. There's a synchronization barrier at the start, another synchronization barrier going into your sort shuffle phase. Sorry, I'm going here. And then after you do this large distributed merge sort, another synchronization barrier after the reducers, right? So you have 3 synchronization barriers in each job step for Hadoop. Spark with a lazy evaluation says, let's defer that. And I've been on teams that did really large-scale Hadoop apps before where you would have map, filter, reduce kind of patterns. With Spark, because of the lazy evaluation, you can do essentially the algebraic technique of function composition. All the maps get slammed together into one stage. And you're eliminating all these synchronization barriers, or not all, but many. So it's a lot like it's a lot like pipelines on a processor. You want to get rid of the wait states. You want to warm up the cache. And so because we have a better generation of hardware now, we can eliminate those wait states, which starts to service this. Does that answer?
A follow-up question to that. So one big feature of Spark is basically, the recovery is really easy, right? When something fails in between. How does that tie into GraphX? Can you still do that when you're doing large-scale processing on a graph? How do you?
Very, very much so. In fact, that was one of the big learnings when Reynolds Shin and all, when they published about doing the Great Sort Challenge. You do get a lot of failures out on a cluster. It just happens, and all kinds of bizarre failures and unknown states, and things get wedged, and processes just don't talk to each other anymore. So you have to have these distributed systems to be resilient to that. And so the thing that's being leveraged here with the graph processing, certainly we see it. We do see these hotspots. Actually, another point that I should have mentioned, with Hadoop, typically the aggregations that I was talking about are done in the reducer phase. Spark, not so much. Spark can actually do aggregations as what we call transformations that are lazy eval. So in that sense, you don't have to have all the values on one node for a given key. You can actually parallelize them. So you can effectively flatten out the key skews. But getting back to your question there, you can think about this. I'll quote Chris Nguyen, who leads Aditao here in Mountain View, formerly Google engineering director. And he made an interesting point. You know, when we looked in the 90s, we had a lot of cheap network, so to speak. We had clusters, we had internetworking, and we could do call by reference across the network. And so URLs became a way of mitigating risk for distributed computing. And systems like Condor would have taken advantage of that. You look, you know, a decade later into the 2000s, suddenly you had very cheap disks. And so it was better to be able to have your own cluster and mitigate risk by doing replication on local disks. And so Hadoop really leveraged that. Well, GFS and MapReduce and Hadoop. When you look into the 2010s, you had multi-core, large memory spaces, SSDs, and the cost curves all changed. And so now it made more sense in a lot of cases to actually recompute as opposed to replicating on disk or calling across the network. So Spark actually uses all three, but that's a very generational kind of trade-off. And so Spark is leveraging this notion of being able to recompute parts of the pipeline because it's faster than making a network call. And so GraphX is going to use that, or any large-scale kind of processing in Spark, because there will be processes that get wedged, and we don't know what state they're in, so we have to go recompute that part.
My understanding of Spark is basically you have to decide what would be a good stage in your pipeline to kind of cache the RDD so that the next flow could pick it up from there. Now when you come to a graph, let's say you're doing single source shortest path.
Right.
What would that be? What would the RDD be? Would it be the transform graph? Would it be something that you save out in between?
Well, the RDDs in this case will be the node RDD and the edge RDD. So the graph is composed of two RDDs. So you would probably want to do the persistence on those RDDs before composing it into a graph. Because of lazy evaluation, Spark is fairly agnostic to this. It's going to go and do its transforms on graphs at a low level, but conceptually we think of it as a graph. So that's where you'd want to put the persistence in. Now, having said that, as data frames get more and more closely integrated with the different components, there's an optimizer in the data frame called Catalyst, which more and more will begin to be used to make automated decisions, such as where to do persistence. Good, great question.
So are there any optimizations built into Spark for repeat workloads? So
Yeah. Definitely. So the notion there is that you have a Spark context in your application, and all the API hangs off of it, and it knows about the RDDs. It's effectively a driver. Your data and your computation is all happening out in the cluster, but the driver is on the client side. And so very much so, we see this case where we will go and do some kind of ETL and have a pipeline where some of the intermediate data products are being cached on the cluster, and then followed up with other pipelines that will go and leverage that. So, of course, the first time you hit the data, you have to read it off disk. It's a known cost. But the subsequent times, if you hit the cache, you get this speed up. You're hitting it at memory speed instead of disk speed. So yes, definitely you get to reuse the RDDs. That's a big, and especially in machine learning or graphs where it's very iterative.
So I was also referring to like repeat workloads in the sense that same kind of ETL happens every day or every so often. I
see what you mean. Well, in that case, what's more, the way that I like to think of it there is you may have a very large kind of workflow overall in your company for what you're doing, but you probably want to decouple it into parts that are more fast-moving than others. And so some things will be repeated and others will be fairly stable. And in that case, rather than having one huge pipeline, you probably want to cut it into parts and then persist the parts, the endpoints. Does that?
Maybe we can.
We might be able to talk offline. That gets back to the earlier question actually about scalding, where some of the concepts are a little bit more evolved and cascading.
So one question add-on to that is how do you, is there any best practices for the time series data when it comes to? For
time series data? Well, interesting. depends. I mean, if you're looking at time series in terms of like Spark streaming, where you've got a microbatch and you're applying based on some microbatch window, I definitely can go into that best practices as far as the operations, as well as how to determine your timing intervals. But in terms of time series, do you mean like more of like a the analysis of doing?
Yeah, every day, maybe everyday analysis. That's right.
Everyday analysis. I mean, that's a little bit higher level. Definitely, this fits very well for that kind of processing, but that would be at a slightly higher level of abstraction. So your time series data might be stored in, say, Cassandra. So how, what windows you're accessing, and then RDDs are a very nice abstraction to be able to apply, especially you're looking at as vectors. Does that help?
Yeah.
There are other people who are doing work on top of this, though. I'm the track chair for the data science track at Spark Summit, and there have been some pretty good talks about time series. I may be able to dig up some other ones that are good.
In case of like graph clustering algorithms, how Spark will handle that kind of like iterative, or like most of the times graph clustering and some of the other algorithms is iterative, right?
Right.
So in that case, like the intermediate graphs or like intermediate values are how it is, like, is it persistent or like how it is stored and reused?
Interesting. Well, so because of the persistence of RDDs, then iterative algorithms tend to really pull ahead in terms of performance, as opposed to something else like Hadoop at scale, where iterative, because of the synchronization barriers, you pay a real cost for that. In terms of graphs, there's still the overhead of composing the graph. So if you're iterating and basically destroying and recreating a graph each time, you'll pay a tax for that. But it would still be better than doing it in Hadoop. Does that help? Last question?
Yeah, last question.
No, I was just saying.
It was mainly for the Spark streaming for open, like for time series database.
Great.
So one thing that we have seen with time series database is that there's like high traffic, for which Spark streaming would be perfect because there's an RDD that keeps collecting it over a time window, and then you just do processing, and then you move on, and then you have all this memory SQL and all this stuff.
Right.
But then now, if you have a very low traffic, have you ever seen situations of very low traffic used with Spark streaming, but time series still?
Time series. So would you want to be adjusting the time
Maybe
windows?
one every hour.
Oh, no, definitely those. That's a great question. And that was a little surprising. It was a little counterintuitive for me, but definitely there are those with like really large time windows. It might be on the order of hours or even days. So I have seen that. You just have to make sure that your receivers are very reliable. I have another set of talks about streaming in particular, and there's one that TD and I have both been doing where we go into looking at a streaming app, all the potential points of failure, and how they're being hardened. And so you have to take that into consideration if you have a really long-running process. This is the main thing.
All right. Well, thank you, everyone. Thank you so much, Paco.
Appreciate it.
Hope you had a very nice time here. Hope you learned something. I know I certainly did. And again, we have these talk series every few months. If you'd like to stay in touch, please stop by. I can give you my business card, or you could look us up on our website. We probably need to streamline this process by getting a mailing list or something like this. So if you'd like to be on our future mailing list, please, you can take my business card and send me an email or drop off your business card. I hope everyone had a nice evening. Thank you all again for coming, and thank you very much, Paco.
Thank you very much.